A genuinely splendid and beautiful good day, ladies and gentlemen, and a very warm welcome to the latest new edition of Simply Electric. And today, we're going to delve deeply into the comprehensive topic of thermal management in electric vehicles. Specifically, does it truly make sense to have a heat pump installed in an electric car for efficiency? We've thoughtfully developed the following detailed outline for our discussion. First, how exactly does an electric car heat up as compared to a traditional combustion engine vehicle? How exactly does the heat pump function simply as a heat pump? What is the unique characteristic of Tesla's Octovalve compared to other conventional heat pumps? And finally, and this is exceptionally crucial for you to consider, is it genuinely even worth it to pay the additional, somewhat higher price for a heat pump? And since you're certainly not the absolute tech expert, as you well know, I've of course brought in an expert once again, and you all should know him from several of our previous videos by now, the very dear Martin Hund. Hello Martin, a warm welcome, good morning to you.
Hello there Ollie, warmest greetings to you.
Yes, today welcomed with roaring applause.
Got lucky?
Yes, thank you so much. That's exactly how it should be indeed. And I'd say let's not talk too much about it. I'll adjust you to the right size right here, and then take a comfortable seat in your spacious back seat, handing over the floor to you.
Thank you very much. Today, I am metaphorically sitting inside a Tesla. We are thoroughly examining in great detail how to efficiently heat electric cars during the notably cold seasons, whilst taking into careful consideration their inherently limited energy resources. The range decreases. What's the deal with that, actually? With combustion engines, of course, it was somewhat simpler. Back then, we had the situation where the engine produced excessive waste heat, much more than one would actually prefer, and that can naturally be employed to warm up the car, essentially without incurring any charge at all. And if you really desire to cool it down, well, then you simply need to connect a specialized climate control unit with the engine. This also generates cold energy, which can of course be utilized as well. With an electric car, I naturally don't have these waste products. I need to install a heater system that's capable of warming up the interior of the car efficiently, without requiring the use or operation of the vehicle's engine at all, for those cold, frosty mornings. So essentially, let's say it's somewhat like a hairdryer that I just install in the air duct. And of course it needs electricity. And if I desire to cool down, I need like an entirely separate device that genuinely and specifically generates the cold. And when I am already incorporating these specific innovative elements into the design of an electric car, it naturally makes sense to approach it in such a comprehensive manner that it not only adjusts the cabin temperature seamlessly, but then it's expanded eloquently into what's termed as advanced thermal management or thermomanagement. This system combines heating, cooling for optimal cabin comfort, enhances battery and motor efficiency, regulates temperature for the ACTC device, boosting vehicle performance and extending component lifespans. And the trick is that I can interconnect them in such a way that I can ensure cooling and heating for all these devices. That's as far as we are going on this particular topic for now. Now let's proceed to discuss the subject of the heat pump. People are saying now the heat pump is regarded as the holy grail of energy saving, especially in the winter. And before diving deep into the intricacies of this topic, we should quickly delve into physics and, in detail, understand how a heat pump works, starting from the fundamental principle. In fact, the heat pump utilizes a physical principle. Depending on the fluid, when it absorbs energy, it evaporates. For instance, water, when I boil it, turns into steam. And when that condenses again, everyone knows this from looking at the bathroom mirror after a shower, then the water builds up and turns back into a liquid. It condenses and, so to speak, releases this thermal energy, becoming liquid again, and it's like a cycle. And if I don't do this in the bathroom, but instead install it into a water piping system or into a conduit system accordingly, then the whole thing looks like this. That's where I have the spot where the water is evaporated. There's a device for that called an evaporator. And there, where the energy is released once again, where the water condenses, that part is called a condenser. And, to make it a complete and functioning cycle, there's a specialized compressor situated up there, which essentially and effectively pumps the gas through the entire system, operating quite similarly to a standard pump. And up here it's gaseous and down here it's liquid. On the left, energy is absorbed, and on the right, energy is released. That is fundamentally the basic physical principle being actively utilized right here at this specific point in our demonstration. We're familiar with this, for instance, from the refrigerator. Inside the refrigerator, it looks like this. Over here on the left side, that's the part of the refrigerator that's on the inside. There, the heat coming from the groceries that are stored inside is absorbed, and then it's actively pumped further by the compressor. And on the outside of the refrigerator, everyone has seen, if they've looked at the back, there's a cooling grid. That's the condenser where the heat energy is released. And anyone paying close attention here can obviously see from the colors a clue about the temperature. And you can clearly see that in this specific image, much more energy is being emitted than was absorbed right here. How does that work then? Is it being conjured from somewhere, or is a miracle happening? No, the difference is the energy that's released right here is not merely just made up of what has been absorbed here, but also from what I specifically and intentionally input into the compressor as electricity, you see. That means the heat released is equal to the electricity supplied to the compressor plus the added heat. And that really is fundamentally the central concept that defines the heat pump. That means the heat pump holds a significant advantage over both the hairdryer and the heating element, precisely because it isn't simply converting the energy into heat that I'm actively supplying as electricity directly to the compressor, but it also captures additional heat from other devices. And what you see here in this image, this has now been successfully adapted for use in an electric car, in an electric vehicle. I plan to use extra motor energy plus charger and battery surplus for two aims. Firstly, generate heat for comfort in cold. Secondly, ensure steady compressor supply. This boosts the vehicle's efficiency and sustainability, advancing electric vehicle technology and reducing the transportation carbon footprint. But also when it becomes necessary, for instance, for components such as the battery or the motor and even the charger, that means, ideally, I'd really like to have the ability to control every single component inside the car and choose whether it should release some heat at this particular moment because it possesses too much, or if it should rather absorb some heat because it's simply too cold. And for that system to work effectively in an electric vehicle, all these devices must be seamlessly connected with various pipes and hoses to this heat pump circuit, so that I can switch them from one side to the other as needed. And you can see that when you take a look inside such a car. For instance, I have a picture here of the chassis of a Porsche Taycan, which also has a heat pump. And on the considerably larger lower part of the frontal storage area, you can clearly see an impressively extensive amount of pipes, pumps, and valves there. It essentially involves meticulously and precisely connecting every single one of those units to the complex and intricate circuit system designed specifically for the heat pump. In the next image, I'll show you what this all looks like in a Tesla Model 3. Here you can particularly notice on the right side the massive compressor. By the way, quite a lot of people often confuse this compressor with the term known as a heat pump. The heat pump isn't merely this compressor, but rather the heat pump embodies the entire construction consisting of an evaporator and condenser, along with the compressor and a throttle, which, however, is just a very small component indeed. This comprehensive system is designed for efficient heat transfer. Here you can see this compressor. You can also tell from the orange cables that it is indeed powered by the high-voltage battery. From the high-voltage battery, and on the left side you can see a device, a kind of construction that at first glance appears somewhat simpler than the complex piping system of the Porsche Taycan. This invention by Tesla cuts labor, assembly, and material costs in complex piping systems. It uses a simplified design with three main components, streamlining the process and enhancing efficiency and cost-effectiveness in operations, marking a significant innovation. It's basically a subplate featuring a storage tank. It's essentially a screw-on fiber composite box, and on its back sits, and now the term is introduced for the first time, what's dubbed the Octovalve. Octovalve derives from the octopus, which is the sea creature with 8 arms, and if you look closely at the bottom, the Octovalve has 8 different inlets, meaning it can switch 8 lines at once, and here's this round thing. We'll take another look at what this does in just a moment. Now, the thermal management in a Tesla looks like this. But don't worry, I won't explain every single component in detail now. That would be just way too complicated, but merely so you have clearly observed how everything is basically arranged. The green spaces we see up here, along with those green lines, are precisely what I've recently described to you as a functioning heat pump system. So, as you might already see here. The inherent ability to condense and also the distinct ability to evaporate. Here we have the compressor, and now there are two valves here which have a special feature. Namely, by simply turning each and every one of these particular valves carefully, I can effectively change the direction of flow in the entire heat pump system. So I can set it to heat more and I can set it to cool, thereby supplying the interior as well. The area displayed in red here, that is identified as a low-pressure coolant zone, can somewhat closely be compared to what a traditional vehicle possesses as its cooling circuit system. So this is not refrigerator coolant, water coolant, but just water with antifreeze. And here the individual units are supplied with heat or cooling, depending on what is specifically needed. This Octovalve, as you might observe, subtly reveals a hint and indeed possesses a unique, quite intriguing feature worth exploring further. Simply by rotating these two individual discs, which are currently displayed one directly above the other, it becomes feasibly possible to generate precisely 16 unique and distinct combinations of how these specific lines are interconnected with each other. Thus, the vehicle, based on its integrated systems, can decide for every single unit within whether it should be actively cooled at this precise moment in time, and emits warmth, heat, which can then be used inside the cabin again. Or is it actually heated to reach a suitable operating temperature? I can heat up the battery while simultaneously cooling down the engine. Simultaneously, I can exchange heat through the radiator with the external air, either absorbing it or releasing it. And just by turning this device with a very simple yet effective gear motor, I can easily create these exact same possibilities without much effort. Essentially, this innovative system replaces a large number of valves and pumps traditionally used in a conventional setup, simplifying the entire mechanism. So this is indeed a very interesting, attractive invention. Basically, as a driver, you don't notice it, except that both the price and production end up being just cheaper. The question now is the heat pump even worth it? So, as I just mentioned, the heat pump needs electricity just like the traditional heating element, but the difference is I can also extract heat from the outside air. At temperatures down to -10 degrees, the external air around us is, say, surprisingly warm enough, allowing me to use the significant energy within it to efficiently heat the building's entire interior space. Or even the heat from the battery. This means if an electric car is parked with a battery at operating temperature, it retains warmth for many hours afterwards because it's well insulated. And this specific temperature can be employed, for instance, to aid in warming up the currently cooled down interior of the vehicle during the initial few minutes, thus helping it to heat up a bit faster. This way the battery doesn't cool down completely, but it might lose about 10 degrees. But still, it really speeds up the warming of the interior space, and that's obviously a valuable help. This ensures that there is a significant energy advantage of the heat pump over the traditional heating element, of between 5 and 15%, depending on whether the vehicle fully utilizes all the capabilities of the heat pump, and of course also depending on the external temperature conditions, how the situation is, the exterior temperature, and the current temperature inside and around the vehicle. So one might well say a heat pump is mainly worth the investment. If I consistently drive a certain distance, on short trips, I have to add so much heat that the heat pump barely makes a difference, because if the outside temperature is below -10 degrees, the heat pump simply can't absorb any more heat or energy. This means the supply of heat is generated solely by the electricity input, and then the heat pump simply has no more gain. And the whole thing is, when I drive very sportily, when I accelerate hard, go very fast, give a lot of gas, the heat pump hardly has an effect because it barely makes a difference compared to the additional electricity consumption I have because of this driving style. Then I don't save anything at all. On longer distances, if I commute daily and travel 20-30 kilometers, depending on the vehicles, there the effect is earlier. In others, it's later. When the temperatures aren't extremely low and when I drive normally, then I usually have this aforementioned noteworthy energy advantage of between 5 and 15%. Some car manufacturers even advertise 20 to 25%, but to be honest, it hasn't really proven to be true. That's a theoretical value which in practice essentially isn't achieved at all. And something else I found important to mention, the range loss you experience in winter with an electric car, it's not primarily due to the heating, but actually more due to the battery's changed behavior at lower temperatures. So to essentially say, I absolutely need a heat pump to move forward in the winter, that really only functions to some extent. In that sense, one could say the significance of the heat pump at that point is somewhat relativized. It's not exactly the holy grail that currently doubles the range of an electric car. As someone thinking about buying a vehicle, you should carefully consider if the extra expense for including a heat pump is truly justified. It's not a given.
Yes, Martin, many thanks indeed for your detailed presentation. Those were some exceptionally great insights, leading me, consequently, to ask two relatively minor questions. Firstly, is this specific Tesla autopilot system patented, and is it exclusively utilized by Tesla alone? For instance, the Volkswagen Group, do they utilize a different technology? What exactly is the difference there?
Tesla filed a patent on this matter already several years ago. But Tesla is willing, indeed eager, to release its patents. That means when they file for a patent, it's not necessarily about protecting it so that no one else can have access to it, but they allow others to build it just like that. The problem is, no one has managed to do it yet. No one has yet had the idea to replicate it accordingly. Well, I don't really know any other vehicle that has a quite similar design, although this particular model is already the second generation produced by Tesla. So anyone who's truly dived deep into all the technical nuances of the Model 3 knows that the first generation of Model 3, before the recent refresh, they didn't have the Octovalve, but rather they had what's known as the Super Bottle. That was already a first generation of simplification of this circuit, but it was still more complex than the Octovalve. The Octovalve was introduced with the Model Y and is now also available since the Model 3 has the heat pump since the beginning of this year, end of last year.
Yes, Martin, and maybe one last question. We also have many viewers who want to get into electric mobility. Do you have a rule of thumb? Can you make a recommendation? If the desired electric car optionally includes a heat pump, for instance, which is usually offered around 700 euros, do you have a rule of thumb or a recommendation for our viewers to share? When is it truly worth it to spend that money? And when is it actually sufficient to pass on that option? Can you provide us with one brief, concise piece of advice to conclude?
Yes, I'd suggest it really depends on a couple of things. The first is your budget. If the additional expense doesn't significantly impact your budget and you can comfortably manage it, then I would most certainly prefer to have a sophisticated heat pump system installed, as it not only slightly enhances the value of the vehicle, but also potentially increases its resale value quite notably. If you can advertise with a heat pump, because it still remains, regardless of its actual efficiency, a compelling selling and buying point. And the second aspect, I would closely re-examine and reflect on my personal driving habits. So, if I am really just driving into the small town, 5 kilometers there and back just to shop, and otherwise hardly taking any significantly longer trips, and I only need a very small compact car that serves this very specific purpose for me, then you can comfortably do without it. If I'm a daily commuter who actually covers 20, 30 kilometers and more every day, even in winter, in that case, it can definitely be worthwhile to opt for a heat pump because it simply leads to a slightly lower consumption.
Yes, Martin, then I must say a very, very big and heartfelt thank you for this extremely valuable information. And yes, we are already coming up to the conclusion of today's presentation. Yes, that was indeed yet another engaging episode of Simply Electric. Starting with the information, how does a heat pump work? Where does it make sense? Where does the electric car differ from the combustion engine? And I hope you enjoyed this show. You give both Martin and me a big thumbs up for that effort. If you're still not yet a part of the vibrant Simply Electric community, now would be the absolute perfect time to join. Hit the notification bell so you don't miss this and other videos. Well, all that's left for me is to simply say goodbye and see you again. Stay healthy and well, my friends. See you the next time. Ciao. Bye.